So we've already identified what variables we're going to measure. We've come up with a proper design, with a proper sample. We collected our data, we did everything, and now we've reached the point in which we have to actually analyze the data. So what should we do? Well, first of all, descriptive statistics, describe what data we have. And the first thing we should do is always check for consistency, check that everything is correct, everything is how it's supposed to be. So things like no missing values. Whenever we have, for instance, a 0 in some variable, then we shouldn't have any information in some other variable. Everything should be, for example, positive, or everything should be negative, that kind of thing. Make sure that all your data are actually correct, that there's no mistakes anywhere. Everything you can possibly think of. And then after that, we start exploring our data, looking for patterns, looking for anomalies. And we see that we have a lot of outliers in some variable, and that shouldn't be the case. And maybe that tells us something about our study design, or something about how we actually measured, something about our samples. So always take a look at the data from an explorative point of view and try and figure out if there's anything odd in it. And finally, just describe your samples, describe your data. And everything we saw about EDA, so everything about EDA comes in here. So central tendency, dispersion, correlation between variables. Always keep in mind the levels of measurement. So remember when you should use the median, because the mean is not a good idea for example, ordinal variables. Plot histograms, scatter plots, box plots, tables, anything that it's going to help you take a look at the data, take a quick look and start making sense out of it. And hey, many times text is just fine. So you don't need to plot just for the sake of plotting. You can just describe in plain English. It's fine. Many times it's even easier just to say something in English and it's fine. And especially if your data has to do with people, it's very important that you describe who they are, where do they come from, age, sex, education, background, that kind of thing. Because maybe there are some hidden factors in your study, something that we did not think about, something that we did not control, and might be somehow interfering with our claims, with our conclusions. So it's a good idea to always describe who the people are, so that maybe in the future we figure out that there could possibly a bias in our sample, or a missing relationship between, for instance, I don't know, the age and the outcome variable. So always describe your samples, who they are. And once we're done describing our data, we can start thinking about inferential statistics. So everything we have done so far is about a sample of data, a sample of people, for instance, from the whole population in the country, let's say. So we're always computing these statistics from samples which are supposed to represent populations. The target of our study really is not the sample, it's the population. And the point again is that we are going to use the sample to estimate something about the population. And here's where inferential statistics come into play. And what we know is that because we are sampling, there's a certain degree of random error, because we know that if we're interested, for example, in the mean in a population, then depending on which specific sample we pick, we are going to have a slightly different result every time. And what we saw is that we can think in terms of the true population mean plus minus a certain degree of error, and that error is random to us. And so what we have to do now with differential statistics is try to separate what is random error and what is not. So try to separate, so to speak, the signal from the noise. And the point is, if we have a very high degree of error, or our samples are very small, then we are not going to be able to draw reliable conclusions, to make reliable claims about the populations, because, well, there's just too much random error. We are not really sure if whatever effect we are observing, it's really the true effect in the population or just random noise. And so regardless of how much validity our study has, we're going to talk plenty about validity later in these videos, regardless of how good our design is, regardless of how well we measured, regardless of how well we planned the whole thing, if we have too much random error, we are not going to be able to derive reliable claims. We're not going to be able to claim something with confidence. And what we have to keep in mind all the time is that the significance of the effects we observe in a sample are always assessed with respect to the amount of random error. So we might have a very large effect. We might observe a very large effect in a sample, but if we have a very large random error, we can't really say if what we are observing is really the effect of the random error. We're going to see now some example of it. And just by way of illustration, let me talk a little bit about the problem of estimating a population mean, so that we see a couple of characteristics of this problem that might give us intuitions into what's coming in the next videos. So let's say we're interested in some concept of interest, something that we could measure with variable x. Now, what we know is that in the population of interest, in the target population, we have a certain distribution of x. And let's say that that distribution has a mean mu and a variance sigma square. So we're typically interested in figuring out what mu is, what is the average in the population. Technically speaking, how we write this is the expected value of this x, of this variable, equals mu. So that means on expectation, if we draw one member from the population, we are expected to see a value of mu. Of course, there's going to be some variation. It's just on average, it's going to be mu. And how much variation? We write it like this. The variance of this variable equals sigma square. So this is the population of interest. So this has to do, let me write here, with individual observation. Now, really what we do in a study is we draw a sample of people of, say, n, or not just people, anything that we're interested in. It could be patients, it could be countries, it could be plants, it could be cars, it could be anything. But we draw a sample of n from that population, and then we compute the sample mean. So we saw the sample mean, x bar, is just what we typically refer to as the average, right? 1 over n multiplied by the sum of the values. So we're computing here just the mean. And what we saw is that this mean, sample mean, has a distribution, what we called the sampling distribution. And what are the properties of that sampling distribution? Well, it turns out that if we do the math, I'm not going to stop much into it now, we could also think about the expected value of the sample mean. So on expectation, if we draw a sample of n items from the population, what is the value that we should expect from the sample mean? So what we see is that it is precisely mu. And this is very good. So it means that if we draw a sample, then we are expected to have the same mean as in the population. Of course, there's going to be some variation. We know there's going to be some random error, but on average, we are going to observe precisely mu, precisely what we are after. And then how much variation do we have? Then what we saw in the previous video is that the more data we have, then there's more the variation, which is a good thing. The more data, the better. So we can actually quantify a little bit and refer as well to the variation of the sample mean. And it turns out to be the variation in the original sample divided by the size of the sample. And this is very well linking the amount of variation we have in the population, in the thing we want to study, and the size of our sample. The more data we have, then the smaller the variation in the sample mean. And what we saw is this concept of the standard error, which again is just the square root of the variance. You got it here, is in this case sigma over the square root of n. And so what we see here immediately is, again, the more data we have, then the better, because the variation in this sampling distribution in the mean is smaller. And so we know that we are expected to observe mu. So on average, the samples are going to give us precisely mu. And the more data we have, then the closer we should be to this mu. And it turns out that we have these mathematical results that say that as the sample size increases, or as the sample size tends to infinity, then the sample mean will converge indeed to mu. So it will get closer and closer and closer and closer to mu. This is what the law of large numbers tells us. But not only that, it's also telling us that the sample mean is going to be distributed as a normal distribution with mean precisely mu and with variance sigma squared over n. So the variance of that distribution is going to be smaller and smaller and smaller as we increase the sample size. And we know here it's going to be actually something that looks like a Gaussian distribution. This is what the center limit theorem is telling us. And so what we have here are two very good intuitions. The first one is the more data we have, the closer we get to the mean. We are expected to observe the mean over replications of our study. If we keep sampling more and more data, then on average, we are expected to observe the mean. And we could also derive something useful, which tells us how close we're getting to the mean, to actually quantify how much variation we have, how much random error we have, because this is telling us that it looks like a Gaussian distribution if we assume certain things. So based on this, we're going to start now talking about statistical testing and proper statistical analysis, again, following somehow this intuition.